welcome to this tutorial on dynamic memory allocation in C. And my name is Micaela S. Macabulos and I'll be your teacher. And actually today, we're going to take a deeper step into one of the most powerful features of the C language. But before we begin, let's do a quick review of what we've learned so far in C. We started with the basics, which are data types, variable, operators, and control structures. And then we move into arrays, functions, and of course pointers. Eventually, we explored structures and file handling. All those topics build the foundation for today's lesson because dynamic memory allocation is where everything comes together. Once you understand this, you'll see how C gives us a low-level control over memory, something many languages hide from you. And honestly, that's what C makes so special. So today, we're leveling up!
In this presentation, I'll be explaining how memory works inside a C program, why DMA is necessary, how we use functions like malloc, calloc, realloc, and free, and what common mistakes to avoid. I'll also show you a complete code example demonstrating all memory segments in action. So let's begin. In this lesson, we aim to accomplish 5 learning objectives. First, explain how memory is organized in a C program. Second, understand the purpose of dynamic memory allocation and why we need it in real programs. Third, to use malloc, calloc, realloc, and free in practical situations. Fourth, identify common errors when handling dynamic memory, such as memory leaks and invalid access. Finally, apply these concepts by writing and analyzing actual C programs using dynamic memory. Our lesson today is divided into 4 major components. 1. Memory segments in C. 2. Why we need dynamic memory allocations. 3. Malloc, calloc, realloc, and free, or DMA functions. 4th, common mistakes to avoid. Let's begin with memory segments. When a C program runs, memory is divided into 5 major segments. 1. Text segment, data segment, BS segment, stack, and heap. Each one has a specific purpose, and understanding them is the foundation for DMA. Let's start with text segment. This is the area of memory where the compiled machine code of your program is stored. It contains all function definition, all compiled instructions, all constant string literals, read-only data. Here's an example. The arrow shows the literal hello world is stored inside the text segment, but it is not input or output. It is simply stored data used by the program. The output printed on screen is displayed by the terminal, not stored in memory. The text segment is also read-only to protect the program instructions. This example shows that the string literals and code instructions live in the text segment, which is fixed and read-only. Next up is data segment. The data segment stores all global or static variables that have an initial value at compile times. An example: these variables remain in memory for the entire program duration. This visual highlights initialized global and static variables stored in the data segment. Next up is BSS segment. The BSS segment stands for blocking static symbol. It stores global variables without initial values, static variables without initial values, variables initialized to 0. Even without assigned values, memory space still reserved them. This shows an initialized variable placed in BSS segment. Next up is the stack. Whenever you call a function, a new stack frame is created. This stack frame contains local variables, function parameters, return addresses, saved registers. The stack is fast and efficient, but limited. This visual shows local variables and parameters stored on the stack during a function call. Lastly, the heap. This is the area of memory especially used for dynamic memory allocation, which is the main topic of this lesson when you call function like malloc, calloc, realloc, and free. The heap is the memory region used for dynamic memory allocation managed manually by the programmer. Heap example. This visual shows memory allocated using malloc and accessed through pointers. Difference between stack. The stack is fast and structured but very limited. Every time you declare a variable inside a function, it goes to the stack. When the function ends, all those variables disappeared automatically. Meanwhile, the heap is different. It is large, flexible, and persistent. When you call allocate, memory you allocate from the heap stays allocated until you choose to release it. And that is exactly why DMA is powerful and dangerous if used incorrectly. To summarize, the stack is automatic, fast, and temporary, while the heap is flexible, persistent, and programmer controlled. These differences are why we need DMA. We go to why we need dynamic memory allocation. We need DMA in situation where required memory size is unknown to compile time, like user input results from a file, dynamic lists, data coming from sensors, database records, or any situation where the size is unknown until runtime. DMA gives flexibility and allows programs to adapt. The key ideas behind DMA. The key ideas behind dynamic memory allocation can be summarized into four powerful concepts. 1. You choose when you locate memory. DMA allows you to request memory exactly when you need it, giving your program flexibility. Second, you choose how much memory to allocate. If the user needs 5 elements now and 500 later, your program can adjust immediately. Third, you choose how long the memory exists. Heap memory does not disappear after a function ends. You control its lifetime. Fourth, and lastly, you choose when it releases. Memory stays allocated until you free it, giving you responsibility and control. These ideas reflect the core power of DMA: efficient, flexible, controlled memory management. Let's go to malloc, calloc, realloc, and free, in short of DMA functions. Malloc locates memory without initializing it. Here's an example of malloc. This reserves space for 5 integers. The calloc allocates memory and sets all values to 0. This is useful when you clean zero initialized memory. Realloc example: realloc resizes previous allocated memory. This allows your program to extend or shrink memory dynamically. Free example: free releases memory back to the system. This prevents memory leaks and ensures efficient program. We go to common mistakes to avoid. Here are the most common mistakes to avoid when working with DMA and why they happen. First, forgetting to use a free. If you don't free allocated memory, it always allocated independently. Second, accessing memory after it's freed. After freeing memory, the pointer becomes invalid. Accessing it may crash the program. Third, using malloc without checking if it's failed. If memory runs out, this function returns null. Using a null pointer causes an instant crash, overwriting pointers and losing track of allocated memory. Overwriting a pointer that points to allocated memory creates a leak. Allocating the wrong size using malloc. Beginners forget to multiply by size of, causing overflow. Here's the full code. The program begins with global variable. That's the oh sorry. So here's the full code explanation. The function itself is in text segment. Its local variable is stored on the stack. Int local main A is equal to 10, int local main B is equal to 20. These are stack variables. Here's a full explanation of the full code. The arrow shows that this hello text from text segment is a example of text segment. The int data var is equal to 10 is an example of data segment. Int bss underscore var is an example of bss segment. The int stack underscore var underscore in underscore function is equal to 200 is a stack. This two examples is also an stack. Int pointer heap underscore var is equal to malloc size of a int is an example of heap. Why DMA makes you stronger programmer? Okay, dynamic memory allocation is more than a feature. It's a milestone. It's the point where you stop being a beginner and start thinking like a systems programmer. If you understand how memory works, how pointers behave, and how to manage heap allocation, DMA doesn't make you stronger. DMA doesn't make you a better C programmer. It makes you a powerful, confident system level developer. That's all. Thank you and happy learning.